I start again. I'm Laurent Michel from Strasbourg and prepare this BoF with Mireille Louys from Strasbourg and François Bonnarel from Strasbourg, Judith Silberman from IPAC, California, and Dave Morris from Edinburgh, UK. So the topic of the BoF is TAP and data models. It's a bit strange, not usual for an ADAS BoF, because data models is something which is usually done backstage. People build data models to build any sort of application, but then usually we do not present those data models. It's one component of the component block of building services. And IVOA, VO data model are just discussed within the frame of the IVOA. The situation for TAP is a bit the same. I would like to tell a little story. When I prepared this BoF, I remember a TV advertisement I saw a long time ago. There was one guy in an office saying to his neighbor, to his workmate, "Oh, please, what is the brand of your washing machine?" And the guy responded, "I don't know. We never speak about it with my wife because it never broke down. It was a smart way to emphasis on the reliability of that brand of washing machine." And this is the same for TAP. Now everyone is using TAP, is running TAP services. So there is no reason to speak and to develop things about TAP. Now it's very widely used. It's I would say a great success of the IVOA. But if you put two topics together, we can have something which is more relevant for ADAS. Because building a data model is about building an accurate description of the data and an accurate description of the way data can be combined together. And if we add some VO flavor, we can say that it's an accurate description that can be shared by different data providers. And TAP is about retrieving tabular data in a standard ways. But our hope with this BoF is to have a TAP-based service able to provide in combination of tabular data with an accurate description, and this may interest people to use TAP to serve a more complex to serve a more complex data than usual tabular data, as we do usually. So it's not a matter of object relational patterns. There are many intermediate situations where we can take advantage of data models without diving into a few object-oriented paradigms. So in this session, we will present what we can do, what we could do, and as return, we hope to generate some interest for the issues and to initiate discussion where relevant use cases will be put on the table. So I will start with a few slides, and this slide will be interrupted. We'll introduce some other talk given first by Mireille and then by Judith and so on. Sorry. Let's start with another story. Here is a star cluster. So I don't know if people, I see people in the audience who are very comfortable with TAP, but maybe some others are not. So I take time to introduce what is TAP from at least my point of view. So here is a star clusters, and here is an astronomer. And what does the astronomer do? It observes the star clusters night after night. It takes spectra of different observations from all the stars of the cluster. And what you want to do, of course, is to publish this data into that use case on which the BoF is built. Now, how to proceed? So if you want to simply publish a source list, detection list, you can just make simple consearch. Okay. If you want to publish a spectra, you run Spectral Access Protocol, SSIP. Okay, but if you want to put all this stuff in one single services in order to allow people to get the sources of detection and the spectra he took on that star cluster, of course he has to run TAP. So TAP is a bit complicated protocol. It relies on many different things. There was a poster from Mark Taylor showing how difficult it is to validate and to build TAP services, but we have a very good expert, and we have also nice tooling. I mentioned DAX, Volt, or OpenCADC, which are toolkits in Java or Python, very helpful to build TAP services. So the goal of TAP is to build a relational, to make a relational database interoperable. So that's the TAP Access Protocol. So TAP doesn't care of the way data are stored. You have data, you put them in table, and you put on top of them a TAP hat, which makes them discoverable and searchable, interoperable. So it's built on three pillars. There is a REST API to access data, UWS. There is a query language, ADQL, which is a sort of SQL flavor with some astro-specific functions. And there is a format for the query result, which is VO table. You can use other format, but we have to use VO table, which is an XML, a particular XML schema for the people who do not know it. So what does a TAP service look like? Basically, you have on your your data. So my astronomer from before has sources detection, because each sources of a star cluster has been detected several times, and spectra. That's suitable in this example. And what you do to transform your database into a TAP services, you have to build a TAP schema, which is a set of tables located in a specific schema. And these tables contains description of the schema of the tables and on the columns, and on the join we will see later. So the key is that this TAP schema is completely standard, so that a client connecting a TAP services can, with a standard way, browse this TAP schema and guess what he can do to get data. So in this example, the client will access the TAP schema, and you can state a query like this, select star from sources table, where sources.macv greater than 19. Well, macv is a column of the source table, and which has been discovered in this TAP schema. And you will get a VO table. A VO table is a table with a field description which matches, of course, what is described in the TAP schema, and some values corresponding to the data rows selected. And we can do a bit more. We can add to this TAP schema some metadata, which is textual description, or U-type, or X-type, or units, or UCDs. And these metadata, a part of the description, are totally standard. So U-type are somewhere data model references, so I won't say more about this. UCD are quantities describing the quantity stored in the column, and X-type is, I would say, a tip to interpret some complex content of a given column. And unit are standard. So the interest of this, again, when you run a query, you will get a VO table, and this metadata will be added in the description of the field. So you have metadata describing your quantity in a standard way, which is very nice for generic client code. So you do not need to know specific vocabulary for a specific service. And this facilitates the data set comparisons. And again, you can run the same query. So, and now, what we would like to do, if I look at my schema, I have a table of sources. For each of these sources, I have several detections. And for each detection, I have one or more spectra. So we can, of course, put this in TAP by using joins. So that's the fourth part of the TAP schema, which is a join description. So in a relational databases, you can join things as you want. So you are free to do any sort of join. But in a type schema, you say this join is scientifically relevant. So join and describe by a source and a target and the keys, as usual, and also by some metadata, giving some semantic of the joins. In our cases, we have a source table, a detection table, which has been joined with the source, and a spectra table, which can be joined with the detection or with the source. It depends on the way the schema is done. And from this, you can run a query, for instance, putting constraint on sources, on detection, and on spectra. You can build a query with a join, so select sources, detection, and star, and a spectra from sources join with detection and spectra, and with constraint on the sources of the detection and spectra. So it's a bit complicated to write, but if you are in a frame of an application, it's completely feasible, doable. What you get after this query, you will get a VO table, which is denormalized. So you have one row for tuple of sources, detection, and spectra. So in this case, you have source one is in 3 row because you have 2 detection, and the first detection has 2 spectra, and so on and so forth. So it's not necessarily easy to parse, but all the information you need is here. And this is the way that usual relational database do works. So we can do maybe things a bit better. At this point, we are very close to supporting data model because we have standard metadata, which is a part of the accurate description of the data model I talked about before. We have a relationship by join, which it can be served by the detailing service, but I do not take time to speak about this. So you have a one-to-one relationship, there are still a few things missing to really deal with data models on tab. You will see that after, and it is not easy to write queries, and maybe it can be difficult to process. So the first things we did in this frame is to figure out how we could parse, how we could browse in the context of a quick look view on the data, how we could give a more comprehensive view of data that are joined. So there is an ongoing work I will show you in a few slides. The use case is rather simple. You have, I guess you know Simbad. Simbad is the databases used to identify objects and to put different detection in different survey of objects with bibliographic references. And so we build with the student a browser. So in Simbad, you have many tables. I'm looking for, sorry, just a moment. I will maybe show you in a better way. Okay. So here, you get it. So the idea in Simbad, I know that people name the W something, a guy, scientifics, published paper around Antares. So how can I do this? I can just, I have to go in Simbad, and I see here there are a lot of tables in Simbad. So that can be discovered by the tab schema. I see that there is one table named basic, so it's a top level table where I can find the reference of the object, Antares in my case, and there is another table named author. And so I have to discover this, to do some inference to understand this. So now I want to find to join an object with an author. So I have to probably to join these two tables. What I have to do after is to parse the tab schema and to understand the path leading from the basic table to the author table, and I see that I have to go through hasref table and ref table. So it is a 4-step path. And once I've understand this, I can write such a table, such a query, sorry, and doing the join on 3 tables, and then I get its source of result. So it's very it's convenient. Everything is there as data, but we think that we could do better in a frame of a quick look, and then we develop this prototype. So I will show you, it's a work in progress, so it will probably fail. So I connect to Simbad, and so I just get the top level of Simbad, basic, and then I can click on the column and I get all the content of the table. So there are no flux on this star. This is unlucky. So I will take something else than the flux. So hasref, okay, and so on. I guess it's a demo, it's a work in progress, and of course it will fail. And the idea is if I want to put a constraint, so I say I want to put a constraint to look object near Antares. So I have main ID here. I can select any any columns in all the table by using this sort of search bar. And then I put a constraint like, so I learn the name, ILF, let's see, %. And then I can run a query. Okay, that's a perfect demo effect. So spare. So that's, I guess my demo is finished. I don't know why. There is a problem somewhere on the Simbad side and on my side. So anyway, you can see later. So if I can try again later. So so let's continue. I don't know what's happened. I have no time to look at this, of course. And so now, if you continue in this path to improve your system, you can see that the database that has been designed now are just a measurement, and we would like to add some more information on it. For instance, we have very accurate errors, and we have to write this error as a covariance matrices. I mean, there are 3 columns for 1 error, so we have to gather to say the system. This error, the error of the position, for instance, is represented by those 3 columns. The same, so we can get an accurate description of the filter. We would like to add information about the observation. So the VO has model for this. We have our dataset model, we have a Mango model, which is coming soon, I hope. And so can we use this in tab context? The answer is yes and no. It's not straightforward. This is the reason of this BoF, and this is the reason of this long introduction. So what we want to do is to put, in addition to the usual metadata of tab, to add something in tab. I don't know where and how to add them, giving some extra information And the fact that this information does not come with the data, it results from the curation work. So reading a paper, for instance, what is done in CDS, or getting some observational information. And so we have to store this in tabs. It's not easy to do. There is no place for this. Sometimes you can put it in table, but sometimes maybe not. I don't know. So in this sense, the tab schema cannot support model-related metadata. So I cannot say the tab schema, this filter is this data, or this has been taken by using such a filter, and things like this. Things are either included in data or not present in the system. So what we would like to do, this is the main topic of the BoF, is to do some system for data annotations. I have my data here. I have my model-related metadata, so column grouping, complex error, filter, frame, and authorship, and so on. And I want to do, in addition to the usual business of the query engine, I want to do some processing, enhancing my VO table with model annotations. And this is what we are working on and what we want to present to you. And it could look like this by a VO some XML stuff putting into the VO table. So Mireille will talk about this, but there are other solutions. So there are three questions about storing a data model in tab, in addition to storing the data itself. You have a problem with the first question is the curation, how to give the service the item it needs to annotate data. So as I said before, it's a curation issue out of the scope of the standard. We have the querying processing, how to enable a service to annotate data. So Mireille is just giving to you a first approach, and Judith just after a second approach. And the third part is the user query, how to retrieve this model-related data. So I will give a few slides on behalf of Dave. So I will give so is there any question? So I talk much now. Is there any question on this presentation? So no, I stop sharing my screen and I give the screen to Mireille. Mireille, are you able to?
Yes. So I will share my screen.
Are you allowed? Are you enabled to do it first?
It seems yes.
Okay, fine.
Okay, so do you see my screen now? Is it correct? Okay, so I'm Mireille Louys, working at CDS from the University of Strasbourg, and I will show you some work we have done last spring in the context of an internship with a student. And the idea was to develop this annotation of information coming from a model into a tab service, and to do this on the fly. So you have the context explained by Laurent just before. So the goal is to insert an XML representation of data model elements on top of a VO table response coming back from a tab service. And we have restricted the frame of this exercise, dealing only with a catalog of astronomical sources. So I will show you an example on just a small table. And we bind we annotate this catalog data with data model information that comes from what is usually covered in a catalog of astronomical sources. models describing coordinates, flux, and redshift. And for this, we have 3 data models in the IVOA that do the job. Coordinate, chords, measure, photometry data models, for example. So these are the building blocks, the smallest elements that cover these concepts. And these elements can be bound together, organized in the Mango data model, which is a work in progress, so that we aggregate these different features measured for one source into a kind of tree describing a source. And so for the source, we can bind the measurements and also some associated data like light curves, time series, SED, these kind of things. And the goal was to represent and embed the description of model elements in XML and within the TAP response. So all has to fit into a VO table. And by doing so, we are compliant with the TAP output. So just to summarize the annotation scenario, in green, you have the usual way a TAP service is working. So on left, I have the TAP client. On the right, I have the TAP server. And the green parts is the usual functionality. The client sets up a query in the query editor. It sends the query to the TAP server, and then the TAP server processes this query, finds through the TAP schema the various columns interesting for the query, and selects the different rows. In orange, I have put the additional work done during this internship. We have programmed a mapping engine, which will add the data model information. So if you look at the machine readable model description that we now have in the IVOA, all the models that I'm talking about, they are already described in an XML format, which is called VODML XML. So from this format, we can extract a dictionary of XML components that I show here. Do you see my mouse? Where? Okay. So here I have separated building blocks representing in XML what is a position, what is a flux, a magnitude, a redshift, a proper motion. And these building blocks are wrapped together in the Mango data model as parameters of one source. So this is the XML description on the model side. And on the data provider side, what we need is the binding of one column with respect to one data model object, data model snippet on the left side. So this configuration is prepared by the curator, which in a Json profile in our exercise. And it allows to bind for one column to which sleeve of the model it belongs in a very simple description. So the prototype is written in Java. It builds the XML annotation block by browsing the dictionary of XML components. And it appends to the annotation blocks the corresponding components that are mentioned into the JSON config and provided by the service. In order to, we had to choose a way to express these model components in XML, and we have exercised an ongoing work, which is the definition of a mapping syntax called model instance in VO table for this work. So once the annotation block is finished, we can insert it into the VO table response and to do so, we have used the Volt tab library developed by Gregory Mantelet. And in this tab library, we have overloaded one class, which is the right header class, so that we can insert this XML annotation block into the VO table. I have put the links on the GitHub repository so that you can know more about these developments. So the prototype, the very short demo, I will show you, fingers crossed. So what can you see? Probably. I will show you our short prototype. This is first in tab handle, because it's easy to show you the columns of the tables. So this is the address, the HTTP link to the prototype. It's very basic. You see, it's a tab server, and we have one table column to play with. It's an example extracted from the Chandra catalog, the last version of the Chandra catalog, a very simple table we have prepared where you find these columns. So what is interesting here, we have a source identifier here in this column. And then we have two coordinates in ICRS to locate the source. And then we have another position in galactic here with an error on the position here. And the error is expressed in an ellipsoid shape with 3 parameters. And then added to that, we have 3 fluxes in various bands, in various filters, and we have 2 hardness ratios. So typically what we can find in an X-ray catalog. What we want to add now is to bind these positions, flux and hardness ratios as parameters expressed in the Mango data model. So if I demonstrate now our small prototype, here is the page to launch, to send a query. So I will select this format, VO table TD. I will ask all the elements that are into my table. So it's called Chandra table, although it's only an example. And then I launch it. I get this this file. And sorry. And here you get a result where, so it's a typical VO table. And at the top of the VO table, I have a VO DML block, which contains first a reference to the model encapsulated into this mapping. Then I have a global part where we have gathered all the information about space frame, filters, all the common information to the various measurements. And then here in this section, in the table mapping part, I will have the connection. I will describe a structured tree where you can find all the different Mango object parameters that are highlighted here. And you can find also the connection of the leaves of the tree with the various columns reference. And this I can show you, I think by this. Sorry, ref is. So typically you see here that these two coordinates in ICRS, they land into an attribute of the class in Mango, which is called STC extend long lat position, long lat point. And if I go further, you will see how we link these different, so some of the parameters are not set because they are not present into the table columns. But you will find here also the GLAT columns from the table. They land into an attribute of the of an object in Mango, and I will have the same with the photometric aspect. So these are the errors. The flux is as a counterpart into the model, into a model attribute, and also the hardness ratios, which are described as Mango parameters. So just to finish my presentation. So we show it works, but there is something I haven't shown, which is the JSON profile. You need to understand the way it is. So this configuration, which is prepared by the data provider, it's where we bind the information of a column and the structure of the classes in the data model. So it's another expression of these bindings. It's done once by the data provider, which describes the way that he sees how these columns from the table can be represented in a model object. I think I don't need this anymore. So what we want to do further is to explore the way we can convey these two configuration information, the model classes on one side and the JSON config on the other side. Either we can add them into the tab schema, or we can store them in a file storage local to the server. We need also to articulate better to define a strategy to handle the default values for the XML attributes that are not inserted into the tables, that don't show up in the JSON config, and adjust and we need to adjust the wrapping of the annotation block to the currently developed IVOA mapping syntax. So just to go further and have a proper XML so that the inserting part of the mapping, the VO-DML part I've just shown, would really land into a resource of the VO table to be compliant with the VO table. This just to exercise the idea of inserting into the tab schema, we could have a model component dictionary for the XML model that would look like this: the components in one column, the snippet, the XML snippet in another column, and a data model ID to show the version, the data model name and the data model version. And for the JSON annotation, we can have the resource name, so the table inside the tab server, and the JSON information into the other column. So as a conclusion, this work was a proof of concept. So we have the benefit of the Vault library which allows this insertion of the model. And I also have a poster showing this the different aspects of this work in this conference, and you have the link here. So thank you for your attention.
Thank you, Mireille. It's a nice work, I guess. I see. There is Hugo asking you to put some URLs in the chat. The URL you show up, Mireille.
Okay.
Is there a question on the Mireille presentation? No hand rise. So maybe I give the talk to Judith. We'll present another approach to do something similar. So Judith, you can share the screen. Mireille, you can unshare your screen.
Yeah, I don't know how to do. Oh yeah.
A red button on top of the screen, probably.
Oh yes, sorry. Thank you.
Okay, let's see if I can do this.
Can you share your screen?
I'm working on it.
Okay. Oh.
I think I'm doing it now. Let's see if I can do.
Okay, good.
Present. No, slideshow. Does that look good? Look like
perfectly.
Like a page. Okay, very good. So yeah, this is who I am. I thank the organizers of this session for reaching out. This is actually an abridged version of a talk that I gave at the IVOA conference almost a year ago. So just a warning, there won't be anything new coming up. These are the people who helped get this project going. So just some terminology here to get started. I'll be talking about a query server rather than a tap server, just because our server actually services all sorts of different endpoints, but you can think of it as a tap server. Here's a typical query for the purposes of this talk, which is about column groups. The relevant parts of this query are the columns in the select clause that come from database tables, the database table in the from clause, and the format being VO table. So the interesting part of the query, the geometry, is really not relevant at all to what I'll be talking about. So I'll just point out that the only columns that are interesting to us are those that correspond directly to columns of the database tables. So here's a typical tap response, VO table response. There's a big old resource here of type results. Up top, you have a bunch of fields which correspond to columns. We assign IDs to them in a very straightforward way. So these are what we will use for the ref values to distance ourselves from whatever aliases or whatever strange names the caller might have given to the columns. We will refer to them this way. Yeah, so we have the table, a bunch of columns, and then the data here, the actual values of the response. So column groups are optional elements. That's what I'll be talking about. For instance, we might have one column which contains error estimates for another one, or several columns containing related data. It's really very flexible. And I'll show how we can indicate that connection using a column group. Again, the relationships we're interested in, they will show up in a VO table response as a relationship between columns of that response. But in fact, they reflect a relationship between the columns of the database tables. And so we can store these, we can talk about these groups purely as a relationship between columns of a database table, but they can show up in myriad responses to all sorts of different kinds of queries. We have a restriction that all of the columns in a group have to belong to the same database table. So there are three. Actually, maybe it would be nice if I didn't have this thing up here on the top, but I don't know how to get rid of it. Oh, well, didn't want to do that. Okay, so anyway, there's three stages coming up here. So I'll answer three questions. What do the VO table elements corresponding to a column group look like? How do we introduce a new column group to the query server's repertoire? How do we basically describe a relationship among database columns? And then finally, at runtime, how does the query server decide whether and with what content to add a column group element to a given VO table response? So to answer that first question, there you go. This is it had to be a very small query for me to fit it on one screen here, but you see we still have this resource of type results with the field elements and the data down here. And then there's this new piece now, which is a group. It has an ID, it has a name, it has a bunch of attributes, and it has a description. It also has a list of field refs which point to the fields down here and these IDs that were highlighted in the previous slide. So this one is interested in columns 0, 1, 2, not 3, 4, and 5. That was the answer to question 1. Question 2, how do we tell the query server about a new column group in such a way that it'll be able to display it in responses? So what we do is we've added 2 new tables to the TAP schema, one called URSA groups, one called URSA group columns. You can think of this one as the charter for the group. It describes what the group is for, its purpose, its description, its name. Well, these are the columns of the table. So what's here is the single record from the URSA groups table. So it has all the information you might want about the group except which columns belong to it. So this is the charter, and down here is the membership list. So the columns of this table are table name and column name, which together give a fully qualified name for a database column. And then the ID, the group ID for the group that this fully qualified column name is assigned to. So a typical record, here are a couple of typical records. Notice that a given table name, column name combination can be associated to many different groups. And conversely, many different table name, column name combinations can be associated to the same group. Right now, what we see here is two different columns, an RA and a DEC column from the same table, and they're associated to the same group. And so this is just a close-up. I really wish I could get rid of this thing up here. Oh, look at that. Oh, great. Okay, so there actually is a heading here. This is the group element. If you just a segment from the response that I showed a while back. So this whole part here in yellow comes from that first table, that charter table. All this will never change. If the group shows up at all in the VO table response, this is exactly what the yellow part will look like: the name, the ID, the description. This part down here will vary depending on the order of the columns in the response. There'll always be the same number. We made a design decision that we'll only display a column group if all of the associated columns are represented in the select clause of the query. Okay, let's see, can we go down? Yeah, all right. So, sorry, I missed something. Yes, okay, so that answered that question. And now we're moving on to the runtime, well, the question of how we actually decide what we're going to display. So here, we basically had to make changes to 3 different parts of the life cycle of the query server. I just mentioned the 2 new tables that we insert into the TAP schema. the query server has already been reading and caching values from tap schema tables. Now it will cache the contents of these two new tables as well at startup. And then at runtime, I didn't color this too well, but some of these steps happened anyway, even before the column groups. They would always construct a database call using the cache metadata. Now that we're doing these column groups and also the service descriptors, data links that I'm not talking about at the moment, there's this extra step where the query server decides which of these new elements are called for based on what it has cached and what columns are appearing in the select clause. It makes a database call, which would have done anyway. It builds a resource of type results around the database response, which it would have done anyway. Then there's this added step now of adding, in our case, the new column groups, whichever ones are called for based on the cached information and the select clause. And then finally, it puts it all together. So, oh, wow. Okay, I'll rush through how we do this. So here's what happens at startup. All along, even before we started doing groups, we would always cache results from both the tap schema tables and the tap schema columns tables. So as far as the tables go, every fully qualified table name gets, we have a lookup between the name and the table level metadata. And similarly, there's a lookup from the column name to the column level metadata. Now with our new tables, first of all, the URSA groups table, we make the same thing. So each ID is the key now in a lookup to all the associated attributes and the description from that URSA groups table that we looked at earlier. So here we have two sample groups and their descriptions and names and some stuff about them. So the URSA groups table is treated much the same way as the columns and tables, but the URSA group columns one, the one that shows the membership lists of the groups, this doesn't get its own lookup. Instead, we add, we incorporate data from this table in existing caches or in existing lookups that we've created already. So for instance, the column level lookup already had the description of each column, its data type, blah, blah. Now we've added a new field called the group IDs. So all the groups to which this column is associated per URSA group columns are assigned to a field course that will show up when we look up this fully qualified column name. So that's one place where we store data from here. And then, so in the going the other way around, in the column groups lookup that we just created in the previous page back there, we now add a field that just says how many of the columns from URSA group columns are actually associated to that group. We don't have to know which ones, but we do want to know how many. So that was cache. That's what happens at startup time. And then at runtime, we do a whole lot of metadata prep just to get going. So here's our query. Again, it has a bunch of columns and a table and geometry that we don't really care about, or any kind of constraint that's not too relevant to us. So we start by extracting the lists of the tables and the columns from the from and select clauses. And then we look them up. Each of these is a key to one of the lookups that we created at startup. So the table has also the table level information, and the columns have table level information, of which we'll see more on the next slide. And one more thing we do here is just do a big mapping, keep track of the names in order from the select clause. We note their indices in the list, and then create what will be the ID, the value of the ID attribute for those columns. So specifically, when when we're trying to decide which groups to show, if you look closely at the metadata associated to each of these columns, we find this field of group IDs. So we look through all of the group IDs for all of the columns in the select clause. And for each of these IDs that appears, we make a list of the columns that pointed to it. So we have RA pointing to this one. We have DEC pointing to this one. There are 3 more that you don't see. They're here in these ... And similarly, there's, let's see, this table, this is this thing with the big long name, W4SNR, that's associated to this column, to this group, sorry. So by the time we're done with this, we have, for each group that's represented at all in any of the group ID lists of any of the columns in the select clause, we have a complete list of all of the columns from this query that are associated to that group. We got 5 for this one, but only 2 for this group. And so now we go back to those counts that we cached at startup. This group, which is the first group, had 5. We know that it's supposed to have 5 columns in it. And indeed, we've got all 5 here, 5 distinct columns. So this one, this group is going to be fully represented. And so we are going to go ahead and create an element for it and include that in the VO table response. This other group should have 4 columns there are 4 columns in the database that are associated to this group, and only 2 of them are represented here in this query. So we're not going to bother to create a column group element for this. That was a design decision. It has been questioned. Maybe we'll change that, but for now, that's how it works. So that was the fun part. That now we're just back to life as usual. We make the database call, put together the response from the based on the database response, but we also now will create a group element for each group that made the cut. Each group, all of whose columns are represented. And as we saw before, most of the interesting part of this these group elements came from the cache. We know what they're going to look like. We know what the description is and the ID and all the attributes. The only values that depend on the query are the field ref values, which point to particular columns of the response. So here we are. Here's our query again. We've already figured out which group we're going to show. We created this mapping at startup of, this is like a different list of columns, so the numbers look a little bit differently, but we know how to find each of these 5 columns here in this list. And there we go, a bit of a left down. So this is the familiar ID, name, position, UCD, description. And then here are the values of the field refs which are relevant to this particular query, key to the order in which the columns are listed in, well, the set of indices of the select clause corresponding to columns associated to this group. And then we have it. There's this slide again that shows the group, but now we know exactly where everything came from. And we can check, except I guess I didn't quite match up properly, so we're not going to see all the columns. This is the old list of columns. Sorry about that. I better fix that for the next time. And with that, I think I am finished.
Thank you, Judith. You can see some similitude between both approaches, this shown by Mireille and this and yours. You have a question by Hugo.
Oh, do I? Let me see if I can find the chat. Oh, should I stop? Let me stop sharing.
Sorry, I'll ask this in person. Thank you so much for this rundown on the schema that you guys are using, and it seems to be quite well defined, as I know XML. I have a quick question. So how easy is it to actually host one of these tab services, say at, let's say at, how easy would it be to do that at Scenario, for instance, if we were to decide to, for instance, host catalogs of sources that we have seen in our quality assurance images that's available on our archive. And secondly, how easy would it be to extend the schema to include radio parameters, so spectral indices, rotation measures, fluxes, that kind of thing? So that's my two questions.
Okay, I'm not sure I understand that. I'm very limited to my small view of what what the query server does. But to answer your first question, I think you might be asking whether somebody else could get a hold of our code and start up one of our example. Yeah. So we're working on Dockerizing the query server, which would make it much easier to do that, but we're not there yet. Does that answer the first question?
Thank you so much.
And the second question, I don't think if you're asking whether it's possible to add other information to within the group, within the column group?
So for instance, to define a group that contains radio data, for instance, I think we had a few optical examples. So things like fluxes and spectral indices and rotation measures, that kind of thing. How easy would that be to do inside that inside the schema format?
I can't really picture that. We tried to make the sorry, I looked at the description in the IVOA specs of what appears in a group, and I think all of those attributes are representable. I don't know about representing other kinds of elements. We haven't looked into that, and I don't know if. I'm assuming you know that that's an appropriate place to put it, but I don't know the answer to your question.
May I help to answer Hugo's question? Hugo, I think what Judith has been showing is a generic mechanism which works, which any kind of tables or tab schema which could be implemented. So of course, our mechanism will be working also with radio astronomy tables or whatever, any kind of table it could work.
Oh, I see what you mean. You're saying if I had
as long as it is in a tab service, what she has shown can be applied.
I see. Yeah. So if you have an interesting subset of columns in any one table, you can make a group out of it. Yeah, sorry, if that was the question, I didn't understand. Yeah.
Thank you.
Okay.
Do you have any other questions from the floor here? Doesn't seem to be the case.
We have a question from Mark Taylor on Zoom.
Yeah, thanks, Judith. That was a clear explanation of what you've done. My question is, are you aware of clients or consumers of these VO tables that are doing something useful with the group information that you've put in there?
I'm very glad, or maybe not glad, I'm glad that you asked this question, because I meant to say that the most interesting work remaining is to populate these tables, the URSA group tables, the URSA group column tables. And that is not going well. It would be nice to automate that in some way. I've been waiting for people who actually use these tables who want to see that information to tell me what they want to see. And that hasn't really been coming our way yet. So that's really the next step.
Okay, thanks.
Thank you. So I have to move on. So there is the third question I mentioned before was how to query data, or to tell the server to run annotation, and what a client can ask for annotated data, whatever annotation it is. I will show you this a little after the François talk. There is a third case now. Mireille and Judith presented a way to annotate, to group columns in legacy data. But there is another cases, more object-oriented, which is I have a model, I store it in some way in my tab services, and I want to retrieve model instance. We are in these cases, we are very closer from the object relational mapping. And François is going to present you what he did with the provenance model. So François, sorry, a little change the order of the talk, but I guess we can start now.
Sorry, I was muted.
Can you share the screen?
Yeah. So, can you see it?
Yes, with a gray box in front of it. Okay.
So, yes, I will be talking about having IVOA provenance DM in TAP. How can we do that? So provenance in TAP, why should we have this? Because we have other ways to get provenance information attached to the data. So for example, embedded in the data header, link to the data record via data link or URL in your main table. Retrievable via a service like ProfSAP via the data ID, and then you get all the provenance information attached to that. So in addition to that, provenance metadata, if you put them in a TAP service, will allow to discover data by constraining provenance features. So that is, instead of having the provenance of one given data set, you will be able to discover data sets by their provenance features. It's a reverse mechanism. The issue is complexity of the model. So you have had a nice presentation by Mathieu Servilla yesterday, where the actual usage of provenance data model has been shown. So, but this is the model. So basically what we have to do to map this into the TAP service is to produce one table per class, but it can be a little complex. So that's actually the work that we have done with the ProfTAP project, ProfTAP specification. It's currently an internal draft to the DAL working group. And ProVips at CDS is an implementation prototype. And the examples and this little demo I will show you after are using ProVips. So the TAP schema, I will not show you the whole TAP schema. It will be very boring, but this is, for example, the entity table. So a set of attributes, and their UCD, UType, data type. And this is for the parameter description table, and this one is the parameter table. And we have plenty of these. So let's look at a ProVips example. So ProVips is dealing is tracing the history of IPS data sets for the HST images and also the IPS style. So I start from an IPS style below on the low part, and it's been generated by an activity, and I want to find out all the drizzle images which were used for this to produce this style. So this is with ProfTAP, this is the way we can. This is the way we can we can get this information. So let me show you with so I already preloaded a tab service, the Provips tab service. And oh, sorry. I think I didn't copy it correctly.
You miss a code at the end.
Yeah, I see. So adding the code and submitting. And this is an error. Well, sorry, I don't think I have time to fix that. Don't understand what happened. Oh yes, I see. I have to add the schema name here. No, not there. No, definitely too stupid to make it work. Sorry. I go back to the presentation. Anyway, I had the result in top chat. So what you can see there is that I have, it's denormalized. That is, we have several information which has repeated. And the same columns for different objects come at different places in the table. So let me go back to the presentation mode. So the table is denormalized and there is this loop issue. And we now will try last step provenance by creating a standardized view. So the idea is to have a join as a permanent view in the tab schema. So the columns will have specific names, for example, entity name, entity location, entity common, generating activity name. And I will also have agent role. And I can have either used entity names or used entity list if I want to gather all the used entities in one single field. So the redundancy may be avoided this way. And but if you want everything, you have to manage to create a recursivity process. So this is the view which will be able to produce such things. So it's rather complex command, but of course, if you select on this view, you directly get so in that case, the actual list of entities which have been used to produce the entity which is there is given here. And there is no redundancy because this column contains the IDs of all the entities. Then you have to pick up this and go to a further step if you want. So clear column names for distinct objects and no more redundancy are a success for that, but there is a complex recursivity to manage and you cannot directly retrieve all full chains of provenance. So if you want to go further, there is the tab annotation of a simple table query. Have you seen Mireille's talk? We have also the idea to use renormalized response, and then we can have queries in a service which for instances of a model. So Laurent, on behalf of Dave, will show more about this. I will not speak about this anymore. So this is the renormalized solution. So instead of having a flat table, what I will have is, I think, so instead of having a flat table, I will have as much table as I have classes used in my query. So here is the entity table. So I have the original entity here, E1, and then E1000, E1001, E1002 gives me the used entities. So it's in the same table. But the activity which produced that is only one single activity, so it's there. And the used and it was generated by relationship classes allow me to make the connection between the used entities and the activity, or between the produced IPS file, IPS and the activity. So for this renormalization solution, the first thing is how can we generate this from a tab service? So probably a user-defined function reformatting could do it, but it's not done yet. And we, of course, need to have clients making full usage of multi-table and foreign key mechanism. I may show you that, for example, Aladdin and Topcat are able to load such tables with such VO tables with multi-tables, but they don't create links between them. I think I forgot to mention that there are groups there which are managing the foreign keys between the tables we have to connect together. So we simulate the joint this way. This is a pure VO table standard. It's in the standard. So the other solution, close to what Mireille has shown with the tab annotator, will be to create on top of the VO table, the flat VO table, which is produced by the tab response, an annotation which will be able to show the actual instance tree or instance loop, which we have been producing by the ADQL query. So here, it's actually exactly the table which you have seen. So the header of the table which you have seen at the beginning. And on top of this, you have the main, the first entity, and then linked to that and dependent of that, we have the activity which has been produced, and then the other entities which have been used to produce this IP style. So in order that a client software reading this will be able to distinguish the starting point entity from the other used entities. So it could be a nice solution if we have a tab annotator able to generate annotation for that. We need some client. Will it be generic, able to read any kind of annotation, or specialized for ProfDN? So if you want to have more about discussion on all these strategies, you can look at our poster, Object-Oriented Data Model Strategy in the Context of IVOA Table Access Protocol, and also Mireille's poster, which she already quoted. I don't know, do I still have time to show?
I guess you have 5 minutes left.
Okay, and you still have something to show. So.
Yeah, maybe you can have some question. If, I don't know. Is there a question in the room? You go?
There's a question on Discord here. I can read that out for you if you want. Brent asks, is there a science use case for grouping tab columns? It is not obvious to me since the column info is already in the table, tab schema, column. So what am I missing here?
I can answer. There is the use case. If there are two use cases, one is the one, as François showed, when you have to put together different tables, if you have sources and detection and so on, and also when your quantity relates to several columns. If you want, for instance, a group build an error, as Judith showed, with 3 or 4 columns, you have no way in tab schema to do this. This is the main use cases. And the same in a Vizier service. Sometimes you have to put just column together to say this description is related to this column, and so on. And the only way to do this is to use either a data model or groups. That's the use cases. François, can you? Is there another question?
Yeah, I just wanted to show that I produced the query which I have shown on the slides previously, and I got this answer where we have the starting entity on the left and the generating activity, the agent, and at the end we have the identifiers of the use entities. So okay. I stop sharing.
Okay.
He says thanks here. Yeah, thanks.
Okay, take it again. So the last topic related to this model and tab is how to run queries. So let's suppose we have some model information in our tab service. We have a server enabled to annotate data or to generate proper serialization of these models. And now we want the client to be able to ask for annotation or to ask for not having annotation, for both. So if we look at to ADQL query, it looks like this. We have select something from table where some constraint and columns. And what we need for a model in general way, not in the frame of tab, is something like this. Select model instances from I don't know what, where a constraint and model lives. And if you put them together, this doesn't match. So the problem is simple. IDQL is not suited, or SQL, to deal with object data. So we have to work this around. So we have two cases, searching legacy data, shown by Mireille and Judith, and searching model instances. So I speed up a little bit. So if you want to search for legacy data, so we cannot add a new feature to ADQL because ADQL is a standard widely used, and please do not touch it. So that's the basic rule we have to respect. So, but we can, we have another way to do. We can add qualifier to the tab query URL. If we look at the tab query request, we have the URL, the different parameters, the URL, the request, the query, the language, ADQL, and the format, the table, and select and the query. You send all of this in the URL to your service, and you get the response. Now, what you can do, in possibility, is to say, okay, in the format, I want a VO table with some qualifier saying with a Mongo mapping. For instance, if the Mongo is the name of the model, it could be provenance or no. This could be a seamless evolution of the tab standard, and it could work. And in these cases, what should happen? The user send the query. The query is processed in a regular way, as usual, and the VO table is produced and stored somewhere. But if there is a Mongo mapping request in format parameters, the engine will analyzes the query as done by maybe in a similar way that has been shown by Judith or Mireille, And if the result can be mapped on Mongo, okay, we return an annotated VO table. If it cannot, because, for instance, the columns requested by the model are not present in a query, and then we return an empty annotation. So this is it could be an easy way to make tab to enable tab to support annotated data. And then, if we look now for model instance, as François showed before, it's quite more complicated. In the ideal world, it would be nice to have a full object-oriented query language. Well, so that it's a very big job. This job has been undertaken many times and it never succeeded in the last decades. And there is not enough demand for this. So let's just focus on our use cases. And what we want to do is to retrieve the provenance of a given dataset that are shown by François before. We do not want to get a model instance in an object-oriented database. That's the topic here. So this data can be served by data link, which is a specific service out of tab returning the serialization. It's not the case here, what we are talking about. But we do not need a full feature of query language if we want to do what François showed before by changing a little bit tab. Again, we have our request tab request with URL request language in query. And what we could do is simply to change the language, saying, for instance, VODM, and put a kind of parameter query saying provenance of such a product. I don't know if it's just an idea, something you can think about. It's just to show that it's possible to consider having with a very seamless evolution of the tab query to include the possibility of retrieving I would say model instance or model annotated data. So in these cases, the processing, of course, is very different. If you ask for a VODM instance, you just run a specific processor returning a specific serialization, and otherwise you get in a regular way. That are the two options I could mention to deal with the model at query level for tab.
Hey, 2 minutes remaining.
So yes, I stop here. This is a bit too long to explain this. Just in a few words, we can also imagine to have a regular tab service and to put a specific library, client library, to deal with one model. And in this case, the model is constructed on the client side and with a specific API and given to the user at a Python dictionary or something like this. But the tab service is absolutely standard and regular as shown by François before. So that's the third option. So it's okay. Thank you. Is there a question?
Yeah, there is a question. Let me just grab it quickly. Just give me 1 second here. James asks on Discord, how would a client know if a server supports vote table variants, try and catch errors, or is that going to appear in the capabilities?
This is a very interesting question. So I have not really an answer. In theory, this sort of information could be stored in the registry. So people discover in the registry, but have not investigated how we can do it. And also, we can have, if we add table to the tab schema, we can ask the tab schema if a model is supported. But it's not clear to me how to do it exactly. I guess it's possible, but I have no clear answer to provide.
Okay, awesome. I think we can take further discussion definitely in Discord, and if you can just answer any questions there. We are going to take a 30-minute break now till about 10 a.m. this side. I just want a warm round of applause for this series of presentations. Thank you. Thank you so much.
Just Marcelo, you can put your question on Discord, please.